Now, you will say that why we haven't used the formula for line charge density, for volume charge density, because we are considering a thin sheet of charge, and the sheet of charge is like this, like my hand. In this condition, there is no volume, there is only a particular area, and this is not a length also, this has a particular area. So we are considering the surface charge density. Now let me draw a diagram in this condition. This is your sheet of charge. Okay, these are the sheet of charges. This is the sheet of charge where the charge is uniformly distributed. Now I have already told you what do you mean by uniformly distributed. That is, the charge remain same at all points. So this is a sheet of conductor where the charge is uniformly distributed. It is infinitely long, so we can show it by means of a dotted line because the length is not known. It is very, very long, so it is shown by this dotted line. Okay, now in this condition you have to find the electric field intensity at a particular point. Let's say this point is capital P and this point is placed at a distance, let's say R, from this plain sheet of paper, and we have to calculate the electric field intensity at point P. For every derivation, first you have to consider a Gaussian surface. For the case of plain sheet of charge, what is our Gaussian surface? As you remember that we have already discussed that for the line and plane sheet of charge, the Gaussian surface is cylindrical. So in this condition also, we have to take a cylindrical Gaussian surface. The cylindrical Gaussian surface is placed in such a way so that it encloses the point P inside the cylinder. Now you can see, for instance, this is a cylinder. Okay, this is a cylinder and this cylinder encloses point P inside it. So if we represent, so it is represented like this. Now what we have done, we took a plain sheet of charge and placed inside the cylinder. Now if you look at this diagram, now this diagram tells you about the area vector as well as the electric field intensity. If this is the plain sheet of charge, so the electric field intensity is diverted outward, it is radial. So this is the direction in which it is directed. Likewise, it is directed in the other side also. So electric field intensity is directly perpendicular to it and outward. Similarly, we have to consider in this condition the three symmetrical surfaces of the cylinder. The first symmetrical surface is the curved portion, the second is the top edge, and the third is the bottom edge. Now let's start one by one with first the curved surface of the cylinder. If you notice the curved surface, then this is a curved portion, the longitudinal length of the cylinder, which you can see is the curved portion of the cylinder. Okay, now if we consider the area vectors, the area vector is directed outward. Now you can see here, if I talk about the edges, these are the edges. Okay, in this condition the area vector is directed outward and perpendicular to the plane. So this is the direction of the area vector. Similarly, this is the direction of the area vector. Now if we have to consider a point P, this is a point P. So let's say a very smaller section of the cylinder is considered, and this smaller section of the cylinder is represented as ds. Now if we talk about the curved surface, so in that particular case, you have to first find the flux. What is the flux in this condition? The closed integration of E dot ds. Similarly, if we have to find the E dot ds dot cos theta, theta is the angle between E and the vector A. In this condition, you can see here the electric field intensity is going in this direction and the area vector is going in this direction. What is the angle between the two? The angle between the two is 90 degrees. So cos 90 degree is 0. So in this condition, your answer is 0. So we can say so that the flux provided by the curved surface of the cylinder is 0. So it provides no contribution to the total flux of the cylinder. Now let's see the second part. In the second part, we have to work upon the edges, the top edge, this one, and the bottom edge. In this condition, you again have to check the angle between E and A. This is the major portion of the derivation, that all the derivation is based upon the angle between E and A. I have already told you that what is the direction of E and what is the direction of A, so you have to take into consideration. Now, if I am talking about the edges, in this condition, the area vector is going in this direction. The electric field intensity density provided by the plane sheet of charge is also going in the direction of the area vector. So what is the angle between the two? The angle between the two is 0 degree. Now if we have to find the flux in this condition, so it becomes E dot ds dot cos 0 degree. And what is cos 0 degree? It gives you maximum value because it becomes 1. So from here we will get E dot integration ds. And what is this integration ds? It becomes the whole area, because by integration we mean that ds are combined to form the entire area. So it is represented by capital A. Now the formula modifies to E dot A. Now, I am talking about the edges. That means I am talking about the top edge and the bottom edge. This is the formula calculated only for the single edge. That is either this, either that. If you have to find the total edges, so how many edges are there in cylinder? There are 2 edges. So in that condition, your value is multiplied by 2. So this is the formula when we consider of the 2 edges of the cylinder. Now if you apply a Gauss law, so in this condition it is given by Q upon epsilon naught. Now put the value of Q from this formula. From this formula you can see here that Q is given by sigma into A. Okay, what is sigma? Sigma is a surface charge density. So put this formula of Q and put it in this equation and you will get sigma A upon epsilon naught. Now rearrange the equation to find the value for the electric field intensity. The electric field intensity in this condition is given by sigma A upon 2 epsilon naught into A get cancelled out and your formula is sigma upon 2 epsilon naught. So this is the formula which we have calculated for the case of the plane sheet of charge. Second is the case when we have to consider the point P at the surface of the sphere. That is, point P is placed at the surface of the sphere. Now, in this condition, you can see if the point P comes at this point, like for example, if it comes at particular point, let's say P. So, small r, this small r now turns into this. Small r, it becomes equal to capital R because both the sphere now they coincide each other. In that condition, small r, which is the radius of the outside sphere, and capital R is the radius of the inside sphere. They both become equal. So in this condition, we can write small r is equals to capital R, and now the electric field intensity turns to Q upon 4 pi epsilon naught. Now, it becomes capital R whole square. In the previous you have seen it was small r whole square, but here these two values get equated up, so it becomes capital R whole square. Similarly, we have to go into case third. For the case third, now we are going to consider that the point P is placed inside the shell. So in this condition, you can look at the diagram that point P is now placed inside the charged sphere. Now, so the Gaussian surface is also put inside the charged sphere that passes through the point P. In this condition, now small r becomes less than capital R. And what happened in this condition when we are talking about point P, then we are talking about the electric field intensity. The electric field intensity is related to charge, that is capital Q. If charge exists, then the electric field intensity exists. If charge does not exist, then the electric field intensity is 0. So in this condition, we can see here, this is the Gaussian surface, okay. The charge is distributed along the surface of the outer sphere. So you can see here that no charge is placed inside the Gaussian surface. That is, if we consider this dotted line where the point P is placed, then the charge Q is 0 in this condition because the charge is there outside or on the surface of the sphere and there is no charge inside this particular surface. So in this condition, Q becomes 0 inside the Gaussian surface. And if Q is 0, so the electric field intensity is also 0. So these are the three conditions when we consider the uniformly charged spherical shell. Now, Till far we have studied about these three cases, that is outside the shell, at the surface of the shell and inside the shell, and the various electric field intensity is calculated. Now you can see here that when we consider outside the shell, in this condition small r is greater than capital R. Similarly, we consider the surface of shell, so small r becomes equals to capital R. If we consider inside the shell, so it becomes less than capital R. As the small r is decreasing, you see that the value for electric field intensity is also decreasing and it comes to 0 at a particular point. Now if we have to frame a graph of what we have stated, so the graph looks like this is a y-axis and this is a x-axis. Let's say along the y-axis we have to mark the electric field intensity. Along the x-axis we have to mark the distance, that is small r, and small r is the radius of the Gaussian surface, that is the point where we have to find the electric field intensity. Now let's see the graph how it looks like. In this condition, first we have to start with this point, that is the point of origin. It has the value r is equals to 0. In this particular case small r is 0. Now where is the condition when we talk about the small r is equals to 0? So in this condition we are talking about the third case, because it implies that small r is less than the capital R. It can be 0 also. So now we start from 0 point and let's say there is a point, let's say capital R. At this point the small r becomes equals to capital R. Now we have to find the electric field intensity in this condition. At the point when the small r is less than capital R, that is I am talking about this particular section. At this particular section small r is less than the capital R. So in that condition the electric field intensity is 0. So if we have to draw the electric field intensity, so the electric field intensity in this condition is 0. Now as soon as we reach a point that is small r is equals to capital R, like for example in this point, you can see here the electric field intensity now has some magnitude, and this magnitude represents that this value electric field intensity is no longer 0. It has some magnitude and let's say it lie at this particular point. At this particular point the electric field intensity becomes Q upon 4 pi epsilon naught r square. So as soon as small r turns to capital R, it becomes a point of certain magnitude. So now we can join it by this particular line, dotted line. As soon as we further increase the value of small r, so now in this particular section small r becomes greater than capital R, that is move on to the first part. The small r when becomes greater than capital R, so your electric field intensity is equal to Q upon 4 pi epsilon naught r square. That means what is happening? The electric field intensity is increasing or it is decreasing? The electric field intensity is decreasing. Why? Because as the small r is increasing, so the capital E is decreasing, because capital E is inversely proportional to 1 upon r square. As you can see from the formula, capital E is inversely proportional to 1 upon r square. It follows the inverse square law. So as the value of r increases, the E decreases, and that too square root times. So if we have to formulate it by means of a graph, so what is the graph when we consider a squared portion? The graph is an exponential curve, and for the exponential curve should be decreasing, because we are considering the electric field intensity decreasing with respect to increasing small r. So when we start from this point, this is the point from where we are going to start, because this is the maximum value of the electric field intensity at small r is equals to capital R. From this particular point, the capital E starts decreasing at a rate of inversely proportional to 1 upon r square. So capital E decreases at a rate of 1 upon r square.